And welcome back to Mr. Gregoris Math. Today we're taking a look at our rules for integration. So just to review, integration is indicated by an integrand symbol, and then it's closed off by denoting which variable you're taking the integral with respect to. So the expression that happens in between the integrand symbol and the dx, or the differential, tells you what expression you're looking for the primitive or antiderivative of. So again, if we had like the integral of some function f of x, the result would be some function capital F of x, which is the primitive or antiderivative, and some constant c. Because when we reverse the process, if we were to derive, this would go to 0 because the rate of change of c with respect to x is 0, and this is the primitive, so its derivative would be lowercase f of x. In other words, d capital F of x would be equal to dx, or it would be equal to f of x. And this is what it means to be a primitive. It means that the derivative of the primitive is the expression itself here. So this is just working backwards. Today we're going to take a look at some of the rules of integration now that we've got the notation cleared up. So let's consider one of the rules. So the first rule would be the integral of f of x plus g of x. So what happens when you have a sum of two functions? And this rule is essentially, are integrals distributive? Well, if we think about what an integral actually is, it is an infinite sum of vertical slices. So you're taking vertical slices of f of x and adding them up, and you're taking vertical slices of g of x and adding them up. Well, that doesn't matter which order you add them in because addition is commutative. So we can imagine this as distributing. So this will be the integral of f of x with respect to x plus the integral of g of x with respect to x. Now, if we actually knew functions f and g, we could find their primitives, and we would, at the end, when we're done evaluating this infinite integral, we would end up having a plus c, or a constant of integration as well too. So this essentially lets us know, hey, we can distribute our integration across all of the sum and difference terms. So what does that look like? Well, suppose we had the integral of sine x plus cosine x dx. Well, this would be the integral of sine x dx plus the integral of cosine x dx. Now, our rules for reversing our integrals is we just have to find what function has a derivative of sine of x. Well, that function is negative cosine of x, because the derivative of cosine is negative sine, so that makes this negative times a negative, which would be positive sine of x. Now, this one's going to have its own plus c because it's its own integral. And the integral of cosine x is sine x, because the derivative of sine is cosine. Remember, we integrate forward, and we can always check by deriving backward. And then this is going to have its own plus c as well, too. And so we would be left with sine x minus cosine x. I'm just rearranging the terms so I don't have a negative first. Plus, and there's just a single c. These two c's can be really any real number, so we'll just combine them to make this one c here. And that is an example of using kind of the distributive power of integrals over sums and differences. Now let's take a look at another type. So another type is when you have like a common factor. So if we think of having something like k f of x, where k is a common factor, or where k rather is an element of the reals. Well, this tells us that we can take this k and remove it. So if we have k f of x's, that really means that we have the integral of f of x dx plus the integral of f of x dx plus the integral of f of x dx plus, well, we have k of those. And that's using the previous properties. So we have this k times. So then why don't we just write that as k times the integral of f of x dx. And this is the constant multiple property. So we can take a k that's a coefficient of an expression that we're integrating, and we can remove it from the integral. It's like common factoring. So here's an application of that. Suppose I was taking the integral of 4e to the x dx. So this 4 is constant to the expression. So I can simply remove it and write it as the integral of 4 times the integral of e to the x dx. And that's exactly what we've done. We've taken k out, we've taken the 4 out. We can continue to evaluate this because the integral of e to the x is, of course, e to the x itself. And so we end up with this as our final response, remembering always that constant of integration. So we've got the sum formula that we've used to prove the constant multiple formula. And we've taken a look actually at sines, cosines, and e's. Let's do another example of an integral. So let's do a more interesting example. We'll do an integral that takes up all of our possible terms that we've covered so far. So we'll do the integral of, let's go 4 over x, there's a new one for us, plus 8 e to the x, plus, let's go 3 cosine x plus 10. There. And we'll do that with respect to x. So this is going to be the integral of each and every one of these single terms. So I can consider this term by term, and often students won't write this line that I'm about to write. They'll just skip down to the next line. But I'm going to write the line as the integral of 4 times 1 over x dx plus 8 times the integral of e to the x dx plus 3 times the integral of cosine x dx plus 10, or plus the integral of 10, or 10 integral of 1 dx. Because these are some of the common integrals that I should know. I should know the integral of 1 over x. The integral of 1 over x is ln, so this becomes 4 ln x. I should know the integral of e to the x. As reviewed before, it just becomes e to the x. I should know the integral of cosine. As seen before, it just becomes sine, so I have 3 sine x. And I should know the integral of 1. So the integral of 1 is x. So this becomes plus 10x. And of course, I'm going to add that constant of integration. So far our rules to integration aren't terribly tricky. Let's take a look at another interesting rule. Let's take a look at an expression. We're going to look at it in reverse. So I'm going to take something like 3x squared plus 2x plus 1, and I'm going to take the derivative of this. So when I derive this, if this is f of x, my derivative is, well, the 2 comes down, so I have 6x, and its degree decreases. And then I'm going to have the 1 coming down, so plus 2, and its degree decreases to 0, so plus 2. This one has a 0 as a degree, so the 0 comes down, and the whole term just goes to 0. So here is my function, and here's its derivative. And I think about how would I reverse this back? So reversing the rule, as we went from this direction to this direction, the degree decreased. So actually, when I'm finding my primitives and I'm working backward, instead of my degree decreasing, I'm going to have my degree increasing. So if I had something like an unknown function, let's call this g of x, or maybe I'll let g of x equal 6x plus 2. So I want to, g prime of x. So I want to find g of x by reversing my integration, or reversing my derivative. So as I go up, my degree is going to increase. So I'm going to take a look at, okay, I'm going to have 6x to the power 2, because that degree goes from 1 to 2, plus 2x to the power 1, because that goes up 1. And now I would have to take a look and say, okay, well, if I take the derivative of this, do I get back to this? And I don't. Because taking the derivative, I would have 2 times 6, which would make 12. But I don't want 12. I want 6. And half of 12 is 6. So I'm going to go ahead and divide by 2. And when I do this and I work backwards, I would have, well, the 1 comes down and I have 1 times 2, and that's 2. Oh, so this term does check out. That term's good. It was this term that needed to be divided by 2. And of course, 6x squared divided by 2 is 3x squared plus 2x. And so you can see I can derive the function, or I can integrate its derivative and get back and forth. But there was this problem of this 1 here. This 1 disappeared. It was gone as we went through. So as we went back, we had to assume that hey, there's something that's going to end up being missing here that's going to become some coefficient or some constant of integration. So that's how we integrate polynomials backwards. We increase the degree, and we fit the coefficients. Now, there's a generalized formula for it to fit the coefficients. So let's take a look at that generalized term. So suppose I had something like this. I had my derivative, f of x, and I'm going to let it equal some sort of polynomial. So it's going to be x to the power, let's go a. Okay, it's x to the power a. And I don't know what number a is. Now, working toward a function, if I wanted to get to f of x, what I would need to do is I would need to integrate both sides of this with respect to x, because the integral of the derivative of f of x dx is f of x. So that's going to be giving me my original function, or my value of my integral. Now on this side, I have to find the integral of x to the power a. And as I work backwards, my degree increases. So I'm going to go from x to x to the a plus 1. Because it was x to the power a, but integrating makes my degree increase. So I'm going to increase by 1. Now, if I think about going backward, after I've got the degree increased, going backward, I would be multiplying by a plus 1 to get back to here. But I don't have an a plus 1 multiplied in front. So I need that a plus 1 that was going to come down in front to be canceled out, which is why I'm going to divide by a plus 1. So now if I work this backward by deriving, I would take a plus 1 and I would multiply it down. Those would cancel, and I would subtract 1 to get to x to the power of a. So this is your generalized rule for finding the integral of polynomial terms. Let's just explore that generalized rule again. We'll do something like this. We'll do x to the power 2 plus 3 over 4 x to the power 3 plus 1 dx. So each term, I'm going to do this a term by term. Each term, the exponent is going to go up. So this is x to the power 2, becomes x to the power 2 plus 1, or 3. And I'm going to divide by that exponent. This term, I'm going to ignore the 3/4. And I'm just going to say the exponent's going to go up to 4. And I'm going to divide by 4. But now I have to remember, oh, it was 3/4 as well too. So it's 3/4 divided by 4 times x to the power of 4. This one I had x to the power 0, so it's just going to become x to the power of 1. And I can't forget my coefficient of, my constant of integration. So simplifying, I'd have 1/3 x to the power 3 plus 3/16 x to the power 4 plus x plus c. And that's it for your rules for integration. You now probably can do most of chapter 13. So I do wish you best of luck and enjoy the rest of Snow Day. Don't forget to hit like, subscribe, ring that notification bell so that you can see when we have new videos. See you next time. Take care.